Hello everyone, I'm Hongyu. I'm a second-year PhD student at Princeton, advised by Maria Apostolaki. Today I'm very excited to talk to you about our work, just-in-time logic enforcement. Generative AI has been increasingly adopted to support a variety of networking tasks, for example, data synthesis, telemetry imputation, and so on. In this talk, I will use telemetry imputation as an example. Telemetry imputation takes coarse-grained network signals as input and aims to recover fine-grained network measurements. While GenAI has become progressively more powerful, its probabilistic nature means it still makes mistakes. For example, the imputed bytes could be even larger than the total bandwidth, which is impossible. Or the values imputed by the model don't add up to the total ingress value, which is another mistake. Or we could observe some very small ingress bytes produced by the model, which contradicts the congestion signals from the network. So there is really a pressing need to prevent GenAI from making such silly but critical mistakes. We can formulate these mistakes as violations of logic rules. In this case, I will simplify these logic rules by assuming a monitoring window to be 5, a bandwidth to be 60, the total ingress value to be 100, and we did observe some congestion signals as ACM marked bytes from the network. So now we have this set of simplified rules. The question is, how do we enforce them? Well, there are two main approaches to enforcing rules in machine learning. We can either teach the machine learning model proactively during training by treating those rules as regularization terms on the objective function. Or we can do this reactively by correcting the mistakes made by the model post-inference. In fact, Zoom2Net, proposed 2 years ago at HotNets, uses both. But what's the problem with these two approaches? Well, on the training side, it's limited to differentiable rules because we need to convert them to the loss terms on the objective function. And this conversion process is inherently manual, meaning that if you have hundreds of rules, it doesn't scale. And it doesn't provide any guarantees because the behaviors penalized during training can still appear at inference. And it's a costly process whenever you need to change the rules or add additional rules and so on. On the other side, post-inference correction, it's hard to define some a distance metric to be minimized during this process to preserve the originality of the output as much as possible. And this correction process inherently overrides the underlying data distribution. The last point might not be immediate, so I will elaborate on it a bit further. Here, as we can see, we have our set of rules, R1 to R2, and I want to use a generative model, in this case, a language model, to impute ingress bytes I0 to I4. First of all, the language model makes the decisions on the next values on its own, but as we can see here, it already made a mistake by producing a value larger than even the bandwidth, violating R1, sorry. And actually at this point on, it's no longer possible to satisfy R2 anymore because the values have exceeded 100, violating R2. So what post-inference approach does is it will give the final output of the language model together with the violated rules with some distance metric, for example, in this case, absolute distance to the solver. And the solver will compute the minimum distance it can achieve while making the final output rule compliant. And then it spits out a solution, a corrected solution. So what's the problem with this? Well, there could be a large degree of freedom, right? There could be many such satisfying solutions that have the same minimal distance. And why is this a problem? Well, this process inherently depends on the algorithms used by the solver instead of the underlying data distribution, causing a distribution shift. That's why we propose LeJIT. LeJIT enforces rules just in time, during inference, not too early, not too late. So what LeJIT does is, alongside the language model decision path, it also runs an SMT solver. And the solver takes in the rules they want to satisfy, and given the rules, it decides on which next values are valid. For example, in this case, given R1, we know that the ingress values cannot be negative, and the language model can only choose from the valid values highlighted in green. The partial output of the language model, or the prefix, is fed back to the solver. The solver then decides on the feasible range for the next value, I3. Given the feasible range, the solver crosses out invalid values. The language models then chooses from one of the valid values, and then this process repeats. The solver computes the feasible region for the last value. In this case, we have a global constraint, so the solver has only one valid option, and we know that this final value, the final output of the language model, is rule compliant because we are enforcing the rules step by step. And this process preserves the statistical fidelity because it was still the language model that was making the decision instead of some arbitrary solver algorithm. So to evaluate LeJIT, we use GPT-2, which is a less powerful and very generic model to demonstrate the benefit of enforcing rules just in time instead of just the sheer power of language model. LeJIT turns the same GPT-2 model trained on Meta's data center dataset into either a telemetry imputer or network data synthesizer by enforcing two different sets of rules obtained from NetNormers, a rule mining framework for networking. And in this talk, I will show the results for telemetry imputation, and for data synthesis, please see the paper for more details. So on the top, I will show you imputation accuracy. On the axis is the normalized error for different imputation accuracy metrics. At the bottom, I will show you the rule violation rate, and x-axis is the rule violation rate, y-axis is the different frameworks. So first of all, as we can see, vanilla GPT-2 without LeJIT violates a large number of rules, 140 of them. Simply rejecting invalid samples, so a GPT-2 plus rejection, will result in worse performance because we are literally cutting off part of the imputed distribution. While Zoom2Net performs much better in terms of accuracy, it still violates a large number of rules. By enforcing the same number of rules, the 4 rules manually identified by the authors of Zoom2Net, LeJIT improves upon vanilla GPT-2 but still lags behind Zoom2Net. By imposing all 716 rules, LeJIT performs on par with Zoom2Net and guarantees no rule violations. So in this talk, I showed you that generative models don't provide any guarantees because they're probabilistic. So we really need ways to enforce domain rules to prevent them from making critical mistakes. And LeJIT enforces hundreds of complex network rules during inference while preserving statistical fidelity. It also can repurpose the same language model for different tasks by enforcing different set of rules without retraining or fine-tuning. And also, we've demonstrated the benefit of using automatically learned rules instead of using those manually formulated rules. So thank you very much for your attention, and please check out our paper for more details.